Picture the solar system as a shoreline at night. Every planet is a lighthouse, and the time to reach it isn't just distance. It's the kind of boat you're sailing, the currents you ride, and whether you're trying to touch and keep going or slow down and stay. Space doesn't reward straight lines. It rewards patience, timing, and gravity, an invisible architecture shaped by unseen forces capable of slowing a spacecraft into orbit or accelerating it toward the outer darkness. If you're ready, take a moment to like this video and subscribe. Now let's begin our journey across the vast clockwork of the solar system. In the silence after launch, when Earth begins to fall away beneath us, distance stops being a number and becomes a feeling. The roar of engines fades, and what replaces it is not sound but scale. Continents shrink into textures, oceans collapse into colour. The planet that once filled our entire horizon becomes a sphere small enough to hide behind a thumb held at arm's length. It is here, suspended above the world that raised us, that we first understand the question we are asking. How long would it take to reach another planet? At first, the answer seems simple. Measure the distance, divide by speed, solve the equation. But space is not a highway stretched flat between destinations. It is a moving architecture, a clockwork of orbiting worlds, each racing along its own path around the Sun. To travel from one planet to another is not to draw a straight line across a map. It is to intercept a moving target while you yourself are in motion. Earth circles the Sun at nearly 30 kilometers per second. That is over 100,000 kilometers per hour. Even now, as you sit still, you are hurtling through space faster than any bullet ever fired. Mars moves more slowly, farther out. Mercury moves faster, closer in. Each planet is a runner on a different track, circling the same central flame. If we wish to reach one of them, we must not aim at where it is. We must aim at where it will be. Imagine two runners on concentric tracks. The inner runner moves quickly, completing laps in shorter time. The outer runner moves more slowly. If the inner runner wants to hand something to the outer runner, they cannot simply sprint straight outward. They must time their pace, accelerate or decelerate, and meet at precisely the right point along the curve. Interplanetary travel is this choreography, written not in footsteps but in gravity. This is why launch windows exist. There are moments, sometimes separated by years, when Earth and another planet align in such a way that the journey between them requires the least energy. These windows are narrow. Miss them by days or even hours, and the required fuel increases dramatically. Miss them by weeks, and you may have to wait years for the next opportunity. Space does not forgive impatience. The most efficient pathway between two planetary orbits is often called a transfer orbit. It is not a straight path, but a long, elegant arc, like tossing a stone so that it curves naturally toward its destination. The spacecraft fires its engines not to power itself continuously across the void, but to shape its fall around the Sun. Once set on course, it coasts. In space, without air resistance, motion persists. A brief burst of energy can carry a spacecraft for months. But there is a paradox hidden here. Travelling outward, away from the Sun, is in some ways easier than travelling inward. To reach Mars, Jupiter, or Saturn, we add energy. We speed up slightly relative to Earth's orbit and allow ourselves to drift outward, climbing gently against the Sun's gravity. To reach Mercury or Venus, we must do something far less intuitive. We must slow down. Earth moves quickly around the Sun. If we wish to fall inward toward a planet that orbits closer to the Sun, we must shed orbital energy. We must reduce our speed around the Sun so that gravity pulls us closer. It is like loosening your grip while spinning in a circle, allowing yourself to drift toward the center. But as you fall inward, the Sun accelerates you. You gain speed again, often too much. arriving at an inner planet becomes a problem not of distance, but of braking. In space, braking is expensive. There are no friction pads, no asphalt roads to slow you down. Every reduction in speed requires fuel, careful planning, or the help of another planet's gravity. This is why missions to Mercury can take years, not because it is unimaginably far, but because it is deceptively difficult to approach gently. The deeper we drift into this understanding, the clearer it becomes that travel time is not determined by distance alone. It is determined by velocity, alignment, and intention. Are we passing by? Are we entering orbit? Are we landing? Each goal reshapes the clock. Consider a flyby. A spacecraft can be sent on a fast trajectory that intersects a planet's orbit, gathering data as it rushes past in a matter of hours. The journey might take months or a few years, but orbiting requires surrendering speed, matching the planet's motion around the Sun. Landing demands even more precision. The spacecraft must not only match orbital speed, but descend through atmosphere or fire engines in perfect synchronization. Every added ambition stretches time. There's another tool in this cosmic choreography: gravity assists. Imagine approaching a massive planet like Jupiter. As you fall into its gravitational well, you accelerate. If you arc around it carefully and depart in the right direction, you leave not only with your original speed, but with a small fraction of Jupiter's orbital momentum added to your own. It is as if you grabbed the planet's sleeve as it raced around the Sun and let it fling you forward. This technique has allowed spacecraft to reach the outer solar system in years instead of decades longer. It is not theft, exactly. Jupiter slows by an immeasurably small amount in exchange. The universe keeps its balance. These maneuvers reveal something profound. Space travel is not a battle against gravity. It is a partnership with it. We do not overpower the solar system. We learn its rhythms. We move when it opens a path. And yet, even with perfect timing, even with gravity's help, the distances remain staggering. Light from the Sun takes 8 minutes to reach Earth. Light from Jupiter can take over half an hour. From Neptune, nearly 4 hours. If even light must spend hours crossing our planetary neighbourhood, what does that say about machines built of metal and fuel? Travelling at the speeds of our current spacecraft, tens of thousands of kilometres per hour, reaching the Moon takes days. Mars takes months. Jupiter, years. Neptune, more than a decade. But these numbers, while precise, conceal the deeper truth. Interplanetary travel is not simply about moving through space. It is about moving through time. Months in transit mean months of isolation. Years mean technological endurance. Decades mean generational planning. The spacecraft that arrives at a distant planet may be the product of engineers who began their work in a different era of history. When we ask how long it would take to reach each planet, we're also asking how patient we're willing to be. How long can curiosity sustain momentum? How far into the future can we send our intentions? Back in orbit above Earth, our engines silent, we look outward and see not empty darkness, but a structured expanse. Invisible arcs connect planet to planet. Orbital paths weave like threads in a tapestry. The Sun anchors it all, a gravitational heart holding its family in motion. We begin to understand that every journey outward is an act of trust. Trust in mathematics, in physics, in alignments calculated years in advance. The spacecraft does not constantly correct its course. It follows a trajectory set long before it leaves Earth's gravity. Its future is written in equations, and so is ours. From this vantage point, Earth glows softly beneath us, fragile and complete. It takes just 90 minutes to circle it once in low orbit. A day still lasts 24 hours. Life continues at its familiar pace. But beyond this thin boundary of atmosphere lies a realm where days stretch into months and months into years. The clockwork of the solar system waits. To step beyond Earth is to accept a new measure of time, not the ticking of seconds, but the turning of orbits. Not the rise and fall of daylight, but the alignment of worlds. The question is no longer simply how far away a planet is. The question is, when will the universe open the door? And as we prepare to leave Earth's embrace entirely, aiming our trajectory toward the inner furnace of Mercury and the glowing veil of Venus, we carry with us this first lesson of the cosmic ocean. In space, time is not just distance divided by speed. Time is timing, and the journey has only just begun. Beyond Earth's orbit, as we turn our trajectory inward, the sun grows brighter, not suddenly, but steadily, like a fire that has been quietly stoked. Our destination is the smallest planet in the solar system, a world so close to the sun that it seems at first glance almost within reach. Mercury. From Earth, it appears fleeting, visible only in twilight, low on the horizon, slipping away into glare before night fully settles. It is elusive, never climbing high in our skies, and in that elusiveness lies the first clue to its true nature. Mercury is not merely close to the sun, it is deep inside the sun's gravitational domain, moving faster than any other planet, racing along its orbit at nearly 47 kilometers per second. To reach Mercury is not like sailing across calm water. It is like trying to dock with a ship already speeding along a tight curve around a blazing star. At first, the journey seems simple. Mercury's average distance from Earth can be far less than that of Mars at times. When the planets align favourably, the gap between us can shrink to around 77 million kilometres. In cosmic terms, that is a narrow strait between continents. But interplanetary travel does not measure difficulty in kilometres, it measures it in energy. Earth orbits the Sun at tremendous speed, about 30 kilometres per second. To fall inward toward Mercury, we must reduce our orbital energy. We must slow ourselves relative to the Sun so that gravity pulls us closer. It feels counterintuitive. To go inward, we do not accelerate, we apply the brakes. And yet, as we descend toward the Sun, something remarkable happens. Gravity accelerates us. The closer we fall, the faster we move. By the time we reach Mercury's orbit, our spacecraft is travelling even faster than when we left Earth. This is the paradox of the inner solar system. If we simply aim for Mercury and allow ourselves to race toward it, we will arrive at extraordinary speed, too fast to remain. We would flash past the planet in a matter of hours, unable to stay, unable to orbit, unable to truly arrive. And so the journey becomes a lesson in restraint. The first spacecraft to visit Mercury, Mariner 10, launched in November 1973 and reached its first flyby in March 1974. Just 4 months of travel. On paper, that seems swift. A season of waiting. A single turning of Earth's orbit around the Sun. But Mariner 10 did not stay. It could not. It performed 3 flybys using Venus's gravity to bend its path inward. Each encounter lasted only hours. Mercury revealed itself in glimpses, cratered plains, scarred cliffs, a surface more like the Moon than any other planet. It would take decades before humanity could attempt something more ambitious. Messenger, launched in 2004, did not take 4 months. It took more than 6.5 years to enter orbit around Mercury in 2011. 6.5 years of careful looping around the inner solar system. 1 flyby of Earth, 2 of Venus, 3 of Mercury itself, each pass shaving off speed, each arc tightening the spiral. Imagine circling a drain, not plunging straight down but easing closer with each rotation. That is how we arrived. Each flyby was a quiet negotiation with gravity. Approach too quickly, and the spacecraft would escape back into solar orbit. Approach too slowly, and the mission would fail to gather the needed momentum for the next loop. the sun blazed nearby, its radiation 10 times stronger than what warms Earth. Thermal shields became lifelines. Electronics endured relentless bombardment. Inward is not easier. Inward is harsher. As we imagine our spacecraft approaching Mercury, the sun dominates the sky. Its light is no longer warm. It is oppressive, white, and absolute. Shadows become razor sharp. The sky above Mercury is permanently black, even at noon. There is no atmosphere to scatter light into blue, no clouds to soften the glare, only vacuum, rock, and a star that fills the heavens. A single day on Mercury, from one sunrise to the next, lasts 176 Earth days. Yet its year, the time it takes to circle the sun, is only 88 Earth days. This strange rhythm means that the sun appears to rise, hesitate, even reverse slightly in the sky before continuing its path. Time itself behaves differently here, stretched and folded by orbital resonance. Temperatures swing with equal extremity. At noon, the surface can reach over 430 degrees Celsius, hot enough to melt lead. At night, it plunges below minus 170 degrees Celsius. With no atmosphere to trap heat, Mercury lives in pure contrast, fire and ice separated by the turning of a single world. To stand on Mercury would be to stand on a relic. Its surface is ancient, battered by impacts from the early solar system. Cliffs hundreds of kilometers long reveal that the planet has been slowly shrinking as its core cools. It is a world still adjusting to its birth billions of years later. But how long would it take us truly to reach it? If our goal were only a flyby, only to see and continue, we could do so in a few months given the right alignment and sufficient propulsion. But to orbit, to linger, to map its surface in detail, we must accept years of travel. Years of looping, of gravity assists, of surrendering speed in delicate increments. Mercury demands patience not because it is distant, but because it is deep. And in that depth lies a deeper realization. Travel time in the solar system is not a ladder arranged neatly from shortest to longest. It is not simply Mercury first, then Venus, then Mars. The geometry of motion reshapes the calendar. The energy required reshapes the journey. The smallest planet near the Sun becomes one of the most intricate to reach. As we complete our imagined insertion into Mercury's orbit, the Sun blazing beyond the horizon, Earth is now a bright star in the darkness. Messages from home take minutes to arrive. The scale of our separation becomes tangible. The journey here may have taken years, yet in cosmic terms, it was a whisper. Mercury circles the Sun every 88 Earth days. It has completed more than 50 million orbits since its formation. Our 6-year voyage is a fleeting mark on its timeline, a scratch on ancient stone. And so, as we drift above this scorched, silent world, we understand something fundamental about reaching the planets. The closest destination is not always the quickest. Sometimes the shortest distance demands the longest patience. From here, we turn slightly outward again, toward a planet that glows with soft brilliance in our skies. Venus, Earth's sister in size, a world wrapped in clouds and secrets. Compared to Mercury, the journey will feel almost gentle, but distance is only one part of the story. As we arc outward from Mercury's fierce glare, the Sun softens slightly behind us, though its presence remains commanding. Ahead lies a world that has captured human imagination for millennia. A planet so bright it has been mistaken for a star, rising before dawn, or lingering after sunset like a celestial lantern. Venus. From Earth, Venus appears serene. It is the brightest planet in our sky, draped in luminous white clouds that reflect nearly 3/4 of the sunlight that strikes them. To ancient civilizations, it was a symbol of beauty and constancy. It never strays far from the sun, always near the horizon, glowing steadily against the fading blue. And yet, behind that brilliance lies one of the most extreme environments in the solar system. But first, we must reach it. On average, Venus lies closer to Earth than any other planet. At its nearest, it can approach within about 38 million kilometers. In cosmic terms, that is a short crossing. With favorable alignment and an efficient transfer orbit, a spacecraft can reach Venus in roughly 4 to 5 months. A journey not unlike that first swift arc to Mercury. Yet even here, the path is not straight. Because Venus orbits closer to the Sun than Earth, we must once again reduce our orbital energy to fall inward. We fire our engines briefly, reshaping our path into a long ellipse that dips toward Venus's orbit. Once the burn is complete, the spacecraft coasts. The Sun's gravity does the rest, pulling us inward like a stone gently drawn toward the center of a whirlpool. Day by day, the Sun grows larger in our view. Solar radiation intensifies. The darkness of space feels less forgiving. Venus begins as a brilliant point of light ahead, steady, unwavering. Slowly it swells into a disk, glowing white against the black. Unlike Mercury, Venus is generous in its approach. Its gravity is not as deep within the Sun's well. Matching its orbital speed is less punishing. Many missions have made the journey in under half a year, and yet arriving is only the beginning. From orbit, Venus is breathtaking, a smooth sphere wrapped in thick, unbroken cloud. No continents, no oceans, no visible surface features. It looks peaceful, almost inviting. But those clouds are not water vapor. They are thick layers of sulfuric acid droplets suspended in an atmosphere composed of more than 96% carbon dioxide. Beneath them lies a world transformed by a runaway greenhouse effect so powerful that it has rewritten the planet's destiny. If we descend through the atmosphere, the experience would be gradual but relentless. The upper clouds are surprisingly temperate. Around 50 kilometers above the surface, temperatures and pressures are not unlike those on Earth. Here, some scientists have even imagined future floating habitats, balloons drifting in the golden haze, suspended above the inferno below. But as we continue downward, the pressure builds. At the surface, the atmosphere is more than 90 times denser than Earth's, equivalent to standing nearly a kilometer beneath our oceans. Temperatures climb to around 470 degrees Celsius, hot enough to melt lead, hot enough to cripple most spacecraft within minutes. Landing on Venus is not simply difficult, it is an act of defiance against physics. The Soviet Venera missions in the 1970s and 1980s managed brief triumphs. Several landers survived long enough to transmit images and data from the surface. Grainy photographs revealed a rocky plain under an orange sky. Jagged stones scattered across a landscape shrouded in haze. The longest lasting of these landers endured just over 2 hours before the heat and pressure silenced it. 2 hours. After a journey of months, years of planning, decades of technological development, 2 hours of surface life. Venus rotates slowly and in reverse compared to most planets. A single rotation takes 243 Earth days, longer than its 225-day year around the Sun. If you stood on Venus, the Sun would rise in the west and set in the east, and it would do so with agonizing slowness. A sunrise would stretch across weeks. Shadows would creep instead of shifting. Time behaves differently here. The thick atmosphere traps heat with ruthless efficiency. Long ago, Venus may have had oceans. Some models suggest it once possessed shallow seas beneath a more moderate sky. But as volcanic activity pumped carbon dioxide into the atmosphere and water vapor amplified the greenhouse effect, the climate spiraled beyond recovery. Oceans evaporated, hydrogen escaped into space, oxygen bound to rocks. The planet did not explode into catastrophe. it transformed gradually, step by step, into the furnace we see today. To reach Venus is to encounter a mirror of possibility, a vision of what a world like Earth could become under altered conditions. It is not merely a destination, it is a warning written in cloud and fire. But how long would it take us to stand in its upper atmosphere, drifting among its clouds? With current propulsion, roughly 4 to 5 months, a single season of travel, faster than Mars, quicker than Jupiter by years. In terms of raw transit time, Venus is one of our nearest neighbours, yet the experience of arrival stretches beyond the calendar. Imagine hovering within the cloud layers. Sunlight filters through thick yellow haze, scattering into soft radiance. Lightning flickers within distant storm systems. Winds at high altitudes circle the planet in just 4 Earth days, racing around the globe in a phenomenon known as superrotation. The atmosphere moves faster than the planet itself spins. Below, the surface glows faintly through the murk, a realm of volcanic plains and vast lava flows. Venus hosts more volcanoes than any other planet we know, possibly over 1,000 large ones. Some may still be active. And yet, despite this violence, Venus maintains an almost hypnotic stillness from orbit. Its cloud tops swirl gently. Its brightness remains unwavering. The journey here may take only months, but understanding Venus could take generations. Because Venus forces us to reconsider what proximity means. It is closer to Earth than any other planet. Similar in size, similar in mass. And yet its surface is utterly uninhabitable. A twin separated not by distance, but by climate history. As we lift away from Venus's orbit, watching its bright crescent recede into the glare, Earth lies behind us, a pale blue star among many. The journey between Earth and Venus can be measured in months, but the evolutionary divergence between them spans billions of years, and so we move outward again, toward a world that once held rivers and lakes, where the question is no longer whether we could survive a few hours, but whether we might one day remain. Mars waits ahead, red and patient, whispering a different possibility. The solar system's clock continues to turn. As we leave the brilliance of Venus behind and allow our path to widen outward once more, the sun shrinks slightly in our window. The light softens, the heat relents. Ahead, a faint red ember glows against the black. Mars. For thousands of years it has watched us from the night sky. Steady, rust-coloured, unmistakable. Ancient astronomers traced its wandering path among the stars. Civilizations named it after gods of war. Later, telescopes revealed polar caps and dark streaks that some believed were canals. It has always felt close enough to imagine, and yet reaching Mars is not a matter of pointing and firing engines. It is a matter of timing a meeting between two moving worlds. Earth and Mars orbit the Sun at different speeds. Earth, closer in, completes a year in 365 days. Mars takes 687 days. Like two runners on separate lanes of a vast track, Earth gradually catches up to Mars roughly every 26 months. These moments are known as opposition, when Mars and the Sun sit on opposite sides of Earth's sky, and the distance between our planets shrinks to its smallest. This is the window. If we launch at the right moment, we can place a spacecraft on a Hohmann transfer orbit, a long, graceful ellipse that intersects Mars's path just as the planet arrives. Done correctly, this journey takes about 6 to 9 months, not weeks, not years, but long enough for Earth to fade into the background of the traveller's mind. 6 to 9 months is an unusual span of time. It is longer than any human has ever travelled continuously away from Earth's immediate neighbourhood. It is long enough for seasons to change back home, long enough for distance to become psychological, not just physical. As we imagine the journey, Earth recedes behind us. At first it remains large and luminous, a blue-white sphere marked by swirling cloud systems. Days pass, and it shrinks into a bright disk. Weeks later, it is no larger than Venus appears from Earth. Eventually, it becomes a star. Communication begins to stretch. At closest approach, radio signals between Earth and Mars take about 3 minutes to cross the void. At their farthest separation, that delay can grow to over 20 minutes one way. A conversation becomes impossible. Every exchange becomes a message sent into the future, awaiting its echo. This is the first taste of true interplanetary separation. As the months unfold, Mars grows from a faint red point into a disk marked by subtle surface patterns. Dark basaltic plains, lighter dust-covered highlands, polar caps that wax and wane with the seasons. Unlike Venus, Mars reveals its surface openly. It does not hide behind clouds, it shows us its scars. But Mars does not wait patiently for us. It continues along its orbit. If our timing is even slightly off, we do not simply arrive late, we miss the planet entirely. This precision defines Mars missions. The launch window opens for only a few weeks every 26 months. Miss it, and the next opportunity is more than 2 years away. There are no shortcuts. The solar system's clock must be respected. When we arrive, we face a new challenge: slowing down. Entering Mars orbit requires shedding thousands of kilometers per hour of velocity. Some missions use rocket engines. Others dip into the thin Martian atmosphere in a maneuver called aerobraking, allowing friction to gradually reduce speed. It is a delicate dance. Too shallow, and the spacecraft skips back into space. Too steep, and it risks destruction. Landing is another chapter entirely. Mars's atmosphere is only about 1% as dense as Earth's, too thin to rely on parachutes alone, yet thick enough to generate dangerous heating during entry. Landers deploy heat shields, supersonic parachutes, retro rockets, even sky cranes. Each descent lasts mere minutes, but those minutes determine the fate of years of planning. The journey may take 7 months, the landing 7 minutes. If humans were to travel to Mars, the voyage would be transformative. For over half a year, they would live in microgravity, exposed to higher levels of radiation than any Earth-bound life experiences. The sun would still shine brightly, but it would feel more distant, less commanding. The psychological impact of watching Earth become a faint star cannot be overstated. And yet Mars feels reachable in a way no other planet does. Because Mars has seasons, it has weather, it has day and night cycles similar to our own. A Martian day, called a sol, lasts just 24 hours and 39 minutes. Close enough to feel familiar. The tilt of its axis creates winters and summers. Frost forms on its poles. Dust storms can envelop the planet for weeks, reshaping dunes and darkening the sky. There is something almost recognizable about it. Evidence suggests that billions of years ago Mars was warmer and wetter. River valleys carved across its surface. Delta formations hint at ancient lakes. Perhaps even oceans once glistened under a thicker atmosphere. Today the water is mostly locked away in ice or hidden beneath the soil, but the memory of flowing rivers remains etched into the rock. The journey to Mars is not only about distance, it is about possibility. At 6 to 9 months per trip, it lies within the span of a human life in a way Jupiter or Saturn do not. A crew could depart, arrive, remain for over a year waiting for the next alignment, and then return. Another 6 to 9 months home. The full mission would span roughly 2.5 to 3 years. Years, not decades. And so Mars stands at the threshold between exploration and settlement. It is the first world where the question shifts from can we reach it to can we stay? But even here, the calendar governs ambition. Because once we commit to the journey, we are bound by orbital mechanics. We cannot return at will. We must wait for Earth and Mars to realign. The planets decide when we may come home. This reality reshapes our understanding of travel time. It is not merely about arrival, it is about cycles, departure windows, waiting periods, return arcs. The journey becomes a loop, not a line. As we imagine ourselves standing on the Martian surface, looking up at a salmon-coloured sky, the sun appears smaller than it does on Earth. Shadows stretch longer. Phobos and Deimos, Mars's tiny moons, move quickly across the heavens. Earth hangs as a pale dot, visible only through careful observation. How long did it take to get here? Months. But what those months contain is transformation. The slow departure from Earth's gravity. The silent drift through interplanetary space. The first sight of another world growing larger each day. Mars is not the closest planet. It is not the easiest to reach. But it is the first that feels like a destination rather than a flyby. As we lift from its surface in our imagination and re-enter orbit, we know something has shifted. The inner solar system lies behind us. Ahead, the distances expand dramatically. The gas giants wait beyond the asteroid belt, massive, distant, and patient. If Mars is a crossing of a river, Jupiter is an ocean, and the travel times are about to change from months to years. Beyond Mars, the sunlight begins to thin in a way that is almost imperceptible at first. The warmth still reaches us, the solar panels still drink their fill, but the sense of scale shifts. The inner planets feel behind us now, close, rocky, familiar in their textures and silhouettes. Ahead lies a different realm. Between Mars and Jupiter stretches the asteroid belt, often imagined as a chaotic minefield of tumbling rock. In truth, it is vast and sparse. The asteroids are separated by distances so immense that a spacecraft can cross the belt without ever passing near a single one. It is less a wall of debris and more a museum of fragments, relics of a planet that never formed, kept apart by the gravitational authority of the giant waiting beyond. Even before we see it, we begin to feel it. Jupiter's gravity is a dominant force in the solar system. It contains more than twice the mass of all the other planets combined. It is not merely a world, it is a gravitational anchor, shaping the architecture of everything around it. Comets are deflected by it. Asteroids are shepherded by it. Spacecraft bend their trajectories in its presence. Reaching Jupiter changes the calendar of our journey. Unlike Mars, which can be reached in under a year, Jupiter typically requires far longer. The exact time depends on the path chosen. A fast flyby mission, optimized for speed and assisted by gravity, can reach Jupiter in a little over a year. New Horizons, on its way to Pluto, made the journey in about 13 months. But to arrive with the intention of staying, to enter orbit and study the giant, requires patience. NASA's Galileo spacecraft launched in 1989 and arrived at Jupiter in 1995, taking over 6 years. Juno, launched in 2011, reached Jupiter in 2016 after nearly 5 years in transit. These missions did not travel in straight lines. They looped inward and outward, borrowing momentum from Earth's gravity, reshaping their paths through carefully timed flybys. The reason is simple and profound. Jupiter is far. At its closest, Jupiter lies roughly 628 million kilometers from Earth. At its farthest, over 900 million kilometers. Even travelling at tens of thousands of kilometers per hour, the journey spans years. And unlike the inner planets, Jupiter sits so far from the Sun that solar energy becomes weaker, forcing spacecraft to carry more robust power systems or rely on nuclear generators. As we imagine ourselves crossing this widening gulf, the Sun shrinks further behind us. It is still bright, but no longer dominating half the sky. The darkness feels deeper, more expansive. Earth is now indistinguishable from the surrounding stars. Months pass, then years. Interplanetary space at this scale becomes a meditation on endurance. Systems must remain operational across extreme temperature shifts. Communication delays stretch to nearly an hour round trip. Course corrections are subtle, measured in tiny bursts that adjust trajectories by fractions of a degree. And then at last Jupiter begins to resolve itself, not as a point of light, but as a sphere banded in rust, cream and gold. The first sensation is scale. Jupiter is 11 times wider than Earth. If Earth were a grape, Jupiter would be the size of a basketball. Its volume could swallow over 1,300 Earths. And yet, as immense as it is, it remains only a fraction of the Sun's size. A reminder that even giants have context. Approaching Jupiter feels less like visiting a planet and more like entering a system of its own. Its cloud bands swirl in alternating belts, driven by powerful jet streams that encircle the globe. The Great Red Spot, a storm larger than Earth, has raged for centuries. Lightning flashes within towering storm cells. Auroras shimmer at the poles, fueled by a magnetic field so strong it could engulf our planet many times over. But the most astonishing realization is this: Jupiter has no solid surface. Descend into its atmosphere, and you would pass through layers of gas that gradually compress into liquid states. Hydrogen becomes metallic under extreme pressure, conducting electricity. Deeper still, the nature of matter changes in ways we're only beginning to understand. To reach Jupiter is not to land upon it. It is to orbit it, to skim its upper atmosphere, to study its storms and moons. And the moons, those silent companions, expand the story further. Europa, with its smooth icy crust, hides a subsurface ocean that may contain more water than all of Earth's seas combined. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. Io, streaked in sulfur, is the most volcanically active world we know. Callisto bears the scars of ancient impacts, its surface a frozen record of early chaos. Each moon could be a destination in its own right. The journey to Jupiter therefore becomes layered. It is not just the years spent travelling from Earth, but the additional time required to explore this entire Jovian realm. Orbital insertion alone demands precise timing and immense energy. Jupiter's gravity well is deep. Arriving too fast risks being flung back into solar orbit or plunging too close to the planet's crushing atmosphere. This is where gravity assists reveal their full power. Spacecraft often use Jupiter not merely as a destination, but as a stepping stone. By flying close to the planet and stealing a fraction of its orbital momentum, they can accelerate outward towards Saturn, Uranus, Neptune, or even beyond the edge of the solar system. Voyager 1 and Voyager 2 performed such maneuvers in the late 1970s, using Jupiter's gravity to slingshot toward the outer planets. Jupiter is both a world and a gateway. As we imagine ourselves suspended in orbit above its swirling cloud tops, time feels different. A day on Jupiter lasts only about 10 Earth hours. The planet spins rapidly, flattening slightly at its poles. Storm systems circle in relentless cycles. Yet its orbit around the Sun, takes nearly 12 Earth years. Stand in orbit long enough, and you would watch entire weather systems form and dissolve. The Great Red Spot itself has changed shape over the decades, shrinking gradually, its crimson hue fading and deepening in cycles we're still trying to understand. How long does it take to reach Jupiter? At minimum, just over a year for a swift flyby. More commonly, 5 to 6 years for orbital missions. But those numbers only hint at the transformation that occurs along the way. Because Jupiter marks the point where the solar system's scale becomes undeniable. The inner planets can still feel like neighbours. Jupiter feels like a frontier. The distances beyond it, towards Saturn and the ice giants, expand so dramatically that travel time begins to stretch into decades. As we turn our gaze outward from Jupiter's orbit, Saturn waits in the dim light. its rings catching faint sunlight like a distant halo. The journey from Earth to Jupiter has taken years. The journey beyond will take even longer, and yet standing here in imagination, watching Jupiter's storms churn beneath us, we understand something essential. The farther we travel, the more time itself becomes the terrain. Leaving Jupiter's vast gravitational embrace, we do not accelerate into brightness, we drift into dimness. The Sun, once an overwhelming presence, now feels like a distant lantern. Its light still reaches us, but gently, diluted across the widening gulf of space. The inner solar system has receded into memory. Ahead, faint but unmistakable, a pale oval begins to shimmer. Saturn. Even from millions of kilometers away, Saturn announces itself differently than any other world. Not because of its size alone, though it is immense, second only to Jupiter, but because of what surrounds it. A thin, luminous line encircles the planet like a cosmic signature. The rings catch the sun's weakened light and scatter it, creating a halo that seems almost unreal against the black. Reaching Saturn is not a short expedition, it is a pilgrimage. At its closest, Saturn lies roughly 1.2 billion kilometers from Earth. At its farthest, more than 1.6 billion. The most efficient missions take years to arrive. Cassini, one of the most ambitious planetary missions ever flown, launched in 1997 and entered Saturn's orbit in 2004. Nearly 7 years of travel, years shaped by gravity assists, looping arcs, and patient coasting through deep space. 7 years. Long enough for technologies to evolve on Earth. Long enough for children to grow, for headlines to change, for entire chapters of human life to unfold. The spacecraft departs in one era and arrives in another. As we imagine ourselves aboard such a journey, the experience is one of endurance rather than intensity. After the drama of Jupiter's storms, the crossing towards Saturn feels contemplative. The Sun shrinks to a brilliant star. Solar panels gather less energy. The cold deepens. Instruments must be insulated against temperatures that approach absolute zero. The silence feels heavier here. Communication delays stretch toward 90 minutes round trip. A command sent from Earth arrives long after it is spoken. Responses take equally long to return. The spacecraft becomes increasingly autonomous, making decisions in real time that humans cannot supervise directly. In this region, trust in mathematics replaces immediate control. Months blur into years as the spacecraft follows its pre-calculated arc. There are no dramatic course changes, only subtle adjustments, small thruster burns that nudge the trajectory by fractions of a degree. The path has been written long before arrival. Saturn is moving along its own orbit, taking nearly 29.5 Earth years to circle the Sun. We must meet it at precisely the right point in its vast journey. And then, gradually, Saturn grows. At first, it is only a pale yellow star brighter than the rest, then a disk, then, unmistakably, a world encircled by rings that stretch wider than Earth's diameter many times over. The rings are astonishingly thin, often no more than tens of meters thick, yet they span hundreds of thousands of kilometers. Ice and rock fragments, from grains of dust to mountain-sized boulders, orbit in synchronized precision. From afar, the rings appear solid. Up close, they resolve into countless individual particles, each following its own path, each guided by gravity's invisible hand. Approaching Saturn is less overwhelming than approaching Jupiter. Jupiter dominates the sky with sheer mass and motion. Saturn feels quieter, almost ethereal. Its colours are softer, muted golds and creams. Its storms are less chaotic, though winds in its upper atmosphere can exceed 1,000 kilometers per hour. The most striking feature is a geometric wonder at its north pole, a hexagonal storm pattern, a six-sided jet stream that has persisted for decades. No one fully understands why it holds its shape. It is as if geometry itself has imprinted a signature into the clouds. To reach Saturn is to enter a system of wonders beyond the planet itself. Titan, its largest moon, possesses a thick nitrogen atmosphere and lakes of liquid methane. Enceladus, a small icy moon, ejects plumes of water vapor into space from a subsurface ocean. These moons transform Saturn from a destination into a network of possibilities. Each could demand years of exploration alone. But how long does it take truly to reach Saturn? With current propulsion and optimal alignments, roughly 6 to 7 years for a mission designed to enter orbit. A fast flyby could arrive sooner, perhaps in 4 to 5 years, but to stay, to orbit, to study, to dive between the rings as Cassini once did, requires surrendering speed and accepting the long arc of gravity. The act of orbital insertion is dramatic. After years of silent travel, the spacecraft must fire its engines precisely as it approaches Saturn, slowing just enough to be captured by the planet's gravity. Too little braking, and it flies past into darkness. Too much, and it risks plunging too close. When the burn succeeds, Saturn no longer drifts ahead as a distant goal. It becomes a presence. Imagine hovering above the rings. They glisten like a frozen ocean suspended in space. Shadows from the rings fall across the planet's cloud tops, creating sweeping bands of darkness that move slowly as Saturn rotates. The sun, now so distant, casts a colder light, less brilliant, more delicate. It feels like twilight even at noon. A single day on Saturn lasts about 10.5 Earth hours. The planet spins rapidly, flattening slightly at its poles. Yet its year stretches nearly 3 decades. Seasons unfold over spans long enough for entire research careers to observe only a fraction of the cycle. Time expands here. What felt like a long journey from Earth becomes small against Saturn's own rhythm. 7 years of travel is barely a quarter of a Saturnian season. Storm systems rise and fade over years. Rings may slowly erode over millions. Moons orbit in silent harmony, sculpting gaps and waves in the rings through gravitational resonance. Saturn teaches a new scale of patience. The crossing from Earth to Saturn may take most of a decade, but the phenomena we observe operate on timescales far greater. Rings may have formed hundreds of millions of years ago, and may dissipate in millions more. Moons may harbour oceans that have persisted for eons beneath ice shells kilometres thick. As we look back toward the inner solar system from Saturn's orbit, the sun is no longer blinding. It is brilliant, yes, but modest. Earth cannot be distinguished without magnification. The realm of rocky worlds feels distant and almost fragile. And ahead, beyond Saturn's luminous halo, lie the ice giants, Uranus and Neptune, so distant that the sun becomes a bright star among many. Reaching Saturn takes years, reaching beyond it takes longer still. But in the hush above those shimmering rings, one truth settles gently over us. The farther we travel, the more the journey itself becomes the measure of our ambition. Distance is no longer a barrier, it is a teacher, and the lesson is only deepening as we prepare to cross into the cold blue frontier beyond. Beyond Saturn's luminous rings, the solar system changes character again. The sunlight weakens into something pale and distant, no longer a commanding blaze but a steady glow that barely warms the hull of our spacecraft. The familiar architecture of the inner worlds feels far behind us. The journey ahead is no longer measured in months or even a handful of years. Now, it is measured in decades of intention. The next world waiting in the darkness is Uranus. From Earth, Uranus appears as a faint blue-green point, invisible to the naked eye, discovered not in ancient times but in the age of telescopes. It orbits the Sun at an average distance of nearly 2.9 billion kilometers. Even at the extraordinary speeds of our fastest spacecraft, reaching Uranus typically requires around 8 to 10 years. Voyager 2 remains the only spacecraft to visit it. Launched in 1977, it did not arrive at Uranus until 1986, almost 9 years later. 9 years of silent travel across the widening gulf. 9 years during which Earth continued to turn, seasons passed, governments changed, lives unfolded. The spacecraft did not hurry. It followed a path written long before its arrival, guided by gravity assists and the quiet persistence of momentum. Approaching Uranus feels different from any previous arrival. Where Jupiter roared with storms and Saturn shimmered with rings, Uranus greets us with stillness. It is a pale, almost featureless sphere. Its atmosphere tinted by methane that absorbs red light and reflects blue-green. From a distance, it looks calm, serene, almost asleep. But its strangeness lies not in its colour, it lies in its tilt. Uranus rotates on its side, tipped over by roughly 98 degrees. Imagine a planet that does not spin upright like Earth, but rolls along its orbit like a fallen compass. This extreme tilt creates seasons unlike any other in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. On Uranus, a single year lasts 84 Earth years. If you were born during the beginning of a Uranian summer, you might not live long enough to see the next one. Dawn and dusk are not fleeting events here. They are generational transitions. Time stretches into epochs of light and shadow. Reaching Uranus is not just about crossing distance, it is about accepting slowness. Communication signals now take nearly 3 hours to travel one way between Earth and the spacecraft. A simple exchange of data becomes an exercise in patience. Commands sent from Earth arrive long after the moment of decision has passed. The spacecraft must operate independently, guided by programming and trust. And yet, Uranus is not empty. Though its atmosphere appears smooth from afar, closer observation reveals high-speed winds racing at hundreds of kilometers per hour. Storm systems form and fade. Beneath the clouds lies a mantle of exotic ices, water, ammonia, methane, compressed into strange high-pressure states. Some models suggest oceans of superheated fluid swirling deep within. Its faint ring system encircles it quietly, darker and narrower than Saturn's but no less real. Its moons, Titania, Oberon, Miranda, bear cliffs and fractures hinting at ancient geological upheavals. Miranda alone possesses cliffs so tall they dwarf anything on Earth, frozen testaments to violent past collisions. But if Uranus feels distant, Neptune feels final. Farther still, at nearly 4.5 billion kilometers from the Sun, Neptune orbits in sapphire solitude. Voyager 2 reached Neptune in 1989, 12 years after launch. 12 years to arrive at the outermost planet. 12 years to cross from the warmth of the inner solar system into the cold blue frontier. At Neptune's distance, sunlight is 900 times weaker than at Earth. The Sun appears as a brilliant star rather than a dominating disk. Solar panels become inefficient. Missions rely on nuclear power to endure the long dark. And yet Neptune is anything but lifeless. It is the windiest planet in the solar system. Storm systems rage at speeds exceeding 2,000 kilometers per hour. The Great Dark Spot, observed by Voyager 2, was a vast storm system reminiscent of Jupiter's red spot, but more transient, appearing and vanishing over years rather than centuries. Neptune radiates more heat than it receives from the Sun. Deep within, unknown processes churn, driving atmospheric motion despite the faint sunlight. Its blue colour, deeper and richer than Uranus, reflects methane and perhaps other atmospheric dynamics we are still unravelling. A single day on Neptune lasts about 16 Earth hours, but a Neptune year spans 165 Earth years. If you were to stand in orbit and watch its seasons shift, you would witness changes that unfold across centuries. Storms might form and dissipate across decades. Entire atmospheric patterns might evolve slowly, like tides in a cosmic ocean. And orbiting Neptune is Triton, a captured moon that orbits backward, suggesting it was once an independent body drawn into Neptune's gravity. Triton is geologically active. Geysers of nitrogen erupt from its surface. Beneath its icy crust may lie an ocean warmed by tidal forces. Even here in the outer darkness, motion persists. Reaching Neptune today would take more than a decade using conventional propulsion and gravity assists. And that assumes perfect alignment. Miss the launch window, and years must pass before another opportunity opens. By the time a spacecraft arrives, the world that launched it may feel transformed. And this is where the true meaning of travel time reveals itself. The farther we journey, the more we leave behind, not just in distance, but in chronology. A mission to Neptune is not simply a technical challenge. It is an act of generational continuity. Engineers who design it may not see its arrival. Students inspired by its launch may be the scientists who interpret its data. The voyage becomes larger than any single lifetime. As we drift beyond Neptune's orbit in imagination, the Sun is little more than a radiant point. The solar system feels less like a neighbourhood and more like an archipelago, worlds separated by immense oceans of emptiness. From Mercury's 4-month sprint to Neptune's 12-year crossing, the pattern is clear. The inner planets measure travel in seasons. The gas giants measure it in years. The ice giants measure it in decades of dedication. And yet, even Neptune is not the edge. Beyond it lies the Kuiper belt, then the distant Oort cloud, a sphere of icy bodies extending perhaps a light year from the Sun. To reach its outer boundary with current technology would take tens of thousands of years. Voyager 1 and Voyager 2, humanity's farthest travellers, are only just beginning to enter interstellar space after nearly half a century of flight. 50 years, and they have barely crossed the threshold. When we ask how long it would take to reach each planet, we're really asking something deeper. How far does our patience extend? How long can curiosity endure? What scale of time are we willing to inhabit? Because the solar system does not bend to urgency. It operates on rhythms older than civilization. Worlds turn, storms rage, seasons shift across centuries, and we, brief luminous beings on a small blue planet, have begun to trace the pathways between them. From the furnace of Mercury to the sapphire winds of Neptune, the journey stretches from months to decades. But every mile travelled, every year endured, expands not just our physical reach, but our understanding. The planets are not merely destinations, they are milestones in humanity's slow awakening to scale. And somewhere, beyond Neptune's deep blue horizon, the Sun fades into the greater galaxy, waiting for the next question we dare to ask. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.